Okay, so welcome to our Introduction Networks class today. 10.1.1, that is
No, there was actually 11.5.5.
Okay, 11.5.5. Let me go pull that.
And that took me.
I will tell you that is a pretty long lab. Let me go look at it. And I will tell you, I'm going to also explain to you when I finally get to the IP addressing scheme, which I'm hoping to talk about. Well, I'm going to talk about Wednesday. The way, let's see, 11.6.6, is that it? Yeah.
11.5.5. Yeah.
Well, I don't see an 11.5.5. Is that a packet tracer?
Yeah.
I think she's talking about
that's
the
Networking Academy.
Okay.
It's Networking Academy. It's in the list.
There, yeah. 11.5.5 is up. It's a packet tracer.
Yeah.
Yeah.
Yes, it does take a while, and I will tell you something else. If you don't do it exactly the way they ask, it will not work and will not give you credit for it. You will also notice that the lab itself and the way subnetting is they always tell you when you do VLSM to bring out get the longest or the biggest subnet first. Can we mute?
Yeah.
You can unmute yourself if you have a question, but there you go. Yeah, I think, Karen, I do believe it's yours. It's got an echo somehow. I don't know what it is, but there's an echo there. But one of the things you'll learn is when they're teaching subnetting in this course, when they're doing VLSM, they always ask you to get the biggest slot of addresses in that first subnet that you do. I don't do that. I actually pull it out of the second one, and I'll show you why on Wednesday when I do a VLSM example for you, because I like for my /30s to be .0, .4, .8, .12, .16. And so if you pull your biggest one out of that first, you end up with these weird .8s like .128, .132, and that's just really weird in a networking environment. So I will show you that when I teach you Variable Link subnet masking coming up. But just be aware, there are multiple ways of doing subnetting that will fulfill the requirements of a network that don't have the exact same subnets as what's being asked for in the curriculum. Right. What you're looking for then is you're looking for the slashes. So if it's the right slash notation and it doesn't overlap with another network, it's okay. But the problem with that is when you're doing Packet Tracer is a program that only understands, garbage in, garbage out. So it looks for one particular answer, and if you don't give it to them, then it's incorrect. So we'll go over more of that. But yes, it is, Karen, it is a little bit tough to do because you're so constrained by what it's asking for. So yeah, don't let that bother you.
I have a magic number and a magic sheet that I give to my students. And I said, if you can just always keep a copy of this on your phone, the 10 steps, any kind of question they ask, you can do it, but it doesn't work with yours.
Well,
and
I will tell you something else. I don't use that method because you can't use it on the test. So I'm gonna teach you the 7 holy steps of subnetting, and then we're going to discuss magic numbers and things of that nature. But there's some ways to do things that we can talk about.
They definitely want you to do it from the bit point of view.
Yes.
So everything is bit oriented, as borrowing bits from whatever octet that you're in. So you have to kind of do the math on the 2 to the power 2 to make sure that you're looking for a host or you're looking for the network, which side you're looking on and what bit you need to borrow. So when you get to that, the networking scenario, you're going to really have to know all of that. It's a lot of questions for that.
Yeah. And what I'm really kind of getting into is, let me check these chats real quick, folks. Yep. Server through PTs. Yep. Also, by the way, Michael and Brian are not here today. They both got COVID. So both of them come down with COVID after our trip. So Brian not only got our truck broke into, but he ended up with COVID. So I'm here floating for the team.
Can I ask another question?
Yep.
I know we have not covered VLANs, but when I was in practice, we didn't do a whole lot of subnetting. We did VLAN tagging. And that was because we had so much transition with people. It was easier just to go ahead and move them and then tag the switch. So what do you think about that?
Well, VLANs, and you got to understand a VLAN equals subnet. So if you got a VLAN is a subnet. And so you had to have a different subnet on every VLAN. So that is the rule. VLAN equals subnet. So you were actually subnetting because each individual VLAN had to be a different subnet. Now there is a thing called private VLANs that we don't cover in this class, to where technically you can have everybody on the same subnet, but they can't see each other. That's a special thing that's used typically.
That's what we did.
Yeah,
That's what we did.
Yeah, that's typically used in a data center, to where you've got multiple servers in there, and they're on the same VLAN. They're actually on the same subnet, but they're on different private VLANs. So it's kind of weird. They're on the same network, but they're not on the same layer 2 network. They're actually logically separated from each other by the switch itself. We don't cover private VLANs in this class.
We used to layer 3 switch. It was $25,000, $35,000. It was an expensive switch.
Yeah, we cover mainly the idea that a VLAN equals a subnet.
Okay.
We're gonna, like, for instance, if you had this normally is a class C with /24. So I'm just gonna show you just a real quick how we basically learned to do VLSM. First off, we're gonna borrow 1 bit, which is /25, which we know our magic number is 128. And that breaks it into 0 to 127 and 128 to 255. So I'm basically just breaking this into 2 different smaller subnets by the magic number at that particular slash notation.
Is your magic number 256? Is that what you're using?
No, my magic number here is 128. Because remember, 0 to 127, 128 to 254. So I borrowed 1 bit. So if you borrow 1 bit, what's the value in that first bit position?
128. That would be your increment, your first increment of 128.
Exactly, which is what a lot of people call it the magic number.
Right.
Okay, I see. I use the magic number of 256 and then subtract the subnet mask, and that gives you,
which in this case would be 128.
Yeah.
Yep,
Yeah,
would be 128, because the mask is in this case 128. So now, because the mask of /25 is 255.255.255.128. So the magic number is 128, because you subtract 128 from 256 or 255, really 256, because it's 0 to 255. So our number is 128. I'm going to go over this a great deal, folks. So I don't want to get too far ahead of ourselves right now, because I want to go back and make sure we understand layer 2 addressing, make sure we understand switches and how they work. Because a switch back in the old day, back in the very, very old days, like, in the 90s, which is old days for us. Remember, we used to have these bus networks, and on these bus networks, we had a literal bus, and we had PCs off of it. Okay, so we're gonna do 4 PCs here. We're gonna do it real quickly. We're gonna make some PCs, and we're gonna label them A, B, well, that's B, C, and D. So if A sent something out, what would happen is, obviously, it would go out here and go along the line, go both ways. It'd hit the terminator right here and be dissipated actually as heat. Believe it or not, if you had a heat gun there, you could actually measure the slight increase in heat, because remember, energy is neither created nor destroyed, basic law of physics. So it would have run out here like this. B would have looked at it, went out here, C would have looked at it, and D would have looked at it, and then it would have hit the end. And what they would have been looking for is, they would have been looking in that frame. And remember, in the frame header, we have the destination MAC address that gets put into the frame header. And then we have the source MAC address. Okay. So that's how Ethernet works. And then you have your data here, which is all that data, which is actually all your upper layer information that's stuck in there. And then what was on the very end here? What do we usually have on the very end of a frame? Anybody remember?
File check, FCS.
CRC.
Yep, CRC, or file check sequence. A lot of people call it, it's the cyclical redundancy check. So a little mathematical formula here. These networks were great, they worked great, but they were not highly efficient. So what we ended up doing is we actually ended up trying to create some different methods here. And so what we did, get my tools back here, get my eraser. What we ended up doing was we created a new device, and we created a device called a bridge that we stuck here in the middle. Okay. And now what a bridge would do is a bridge would segment your network into two pieces. And so this bridge, let's say I had 2 ports. So let's just say I had an Ethernet 1 or an Ethernet 0 and an E1, okay? Because these were usually pretty slow speed things. And so this bridge would build a table, and it would be port and then MAC, okay? And so what it would do is it would say, okay, on port E0, it would eventually, by looking at the frames coming through it, looking at the source MAC addresses of frames coming in on E0, it would learn that A, so the MAC address of A and the MAC address of B were on the segment here on the left-hand side. It would then also learn by looking at return packets that the MAC address for C and the MAC address for D were on the right-hand side. And that would allow the frame to actually do things like, or not the frame, the bridge to do things like this. It would be able to say, okay, A is sending something just to B. So that would still come out on the line. It would go out here, it'd go both ways. It would get, obviously it'd go and get destroyed by the terminator. It'd go over here, B would see it, and it would get here to the bridge, and the bridge would look in the table and say, oh, that destination MAC address is for B. Well, B is already on segment 1 over here on my left. So don't forward it over to segment 2. And so by building this MAC address table in the bridge, it was able to segment the network and increase the ability of the network to work, because while A is sending to B here, C can be sending over to D, and they won't interfere with each other. Now, this goes completely off the rails as soon as A sends out a broadcast, because if it sends a broadcast out to the all F's MAC address, which would be 12 F's, which I'm not going to write them all out here, but like you're a cat hissing at people. All right. That broadcast MAC address will never be put in the MAC address table. And so a broadcast, if it goes out, it has to be forwarded out every port except the one it came in on. And so that would have crossed. So bridges were able to make smaller collision domains, but had no effect on the broadcast domain size. All right, questions about that? Anybody ever work with a bridge?
I did. It didn't seem to make much difference in the network speed.
No, not really, but it would, trust me, if you'd have taken it out, you would have noticed, okay? So what we've done now, what does a modern network do? Well, a modern network does this. A modern network says, I don't have bridges anymore, but instead of a bridge, I'm going to make a multi-port bridge. In other words, you know what a switch really is? A layer 2 switch, by the way. I'm not talking about layer 3 switches. I'm only talking about layer 2, which is what we discuss in Cisco CCNA. I'm going to create a multi-port bridge called a switch. I'm going to put these 4 PCs off of this multi-port bridge, which is a switch. Okay. A, B, C, I keep having trouble with B, and D. And this switch is going to build a table, port and MAC. And what it's going to do is it's going to say, okay, on port 1 here, okay, so FA01 is the MAC address of A. Now, by default, when it boots up, it knows nothing. So when it boots up, it's going to be just like the curriculum showing right here. There's nothing in the MAC address table, 0. So if A sends anything to anybody, guess what it has to do? It has to flood it out, all ports except the one that come in on, because it has no clue. But when A sends something, just as soon as A sends something, the switch will look at the MAC address and say, oh, the source MAC of the information coming in on port 1 is the MAC address of A, and we'll put it in the table. And then when one of these devices responds to whatever was sent out, it will say, oh, that was destined for D. Well, D down here on FA04, okay, 04, that's where the MAC of D is. And eventually we'll learn where all of the different MAC addresses are on the switch. And we'll have a table or a MAC address table. And that table will allow it to know exactly where to send things. So once this table is built, the switch can allow A to be sending to D while B is sending to C at the same time. Now, if a broadcast comes in, broadcasts are bad, remember. So if a broadcast comes in destined for all Fs, it's going to come in here. The switch will look at the MAC address table, will not find it, and will then forward it out every port except for the port it came in on. By the way, if a switch ever is given a MAC address it doesn't know, it will always forward it out every port except the one it came in on. That
Are you using F for Ethernet?
Yeah, F fast Ethernet. Fast Ethernet. That's 100 megabit per second link. So FA is 100 megabit. So they start out like this right here with nothing on them in the content addressable memory table, the CAM table. And then they learn slowly by looking at frames going through them. They learn the different MAC addresses on each one of the ports until the table gets fully populated. And then at that point, it can filter frames based upon the MAC address. So let's look down here. I love this activity. I'm gonna try to slide my thing. This is one of my favorite activities in the entire curriculum because it says, determine how the switch forwards a frame based on the source MAC address, the destination MAC address, and information in the switch MAC table. So answer the following questions. Here's the frame. The frame has the destination of 0C and the source MAC is 0E. So I'm gonna look here and find, all right, it's going to 0C. It's from 0E, so down here. My table right now, let's look at what we got here. So, so the MAC address table is already in 0C. So it already knows that 0C is on port FA5. It does not know that 0E is on port FA9. By the way, that's a symbol for a hub, that little thing there. So where will the switch forward the frame? If it comes in to the switch, the only place it's going to go is to FA9, okay? And then when the switch forwards the frame, which statements are true? Switch has the source MAC address, which is currently not in the MAC address table. That is true because if you look right here on port 09, 0E is not currently in the table. So it looks at that source MAC address of the incoming frame, puts it into the table. The frame is a broadcast? Nope, because you'll see the destination is not all Fs. And I know these are shortened MAC addresses, by the way. This is not a full 48-bit MAC address. The frame is a unicast frame will be sent to the specific port only. That is true because it's not going to be flooded because the MAC address that the switch already knows where that MAC address is in the table, 0C, and it's not going to be dropped because the switch is not going to drop it. It just doesn't do that. So if I do check, I should be correct.
Question only from.
What did I do wrong here?
It should go out FA5.
Oh, yep, my bad. Screwed up. FA5. Why did I do 9? I'm a dummy. FA5. There you go. It will go out FA5, not FA9. There you go.
I don't understand. The switch adds the source MAC, which is not currently in the MAC address table, but it is in the table.
No, it's not.
And so
here's the table. Here's the MAC address table for the switch. Notice on port 09, the switch does not have 0E in the MAC address table. So when this frame comes in on 09, the switch looks at it and says, oh, that has a source of 0E. I don't have that in my table. Add that to port 09 or FA9. And then it looks for the destination, which is 0C, and says, oh, that's FA5. Send it directly out FA5. You see that, Kim?
okay, I see it now. Yes.
Okay.
Oh, what does it mean that it's OF in A9?
OF, okay. That means that because there's a hub here, remember a hub is nothing but like physically connecting two devices together. sometime before we got this problem, 0F has sent a frame that the switch has seen. So it already knows about the host 0F. So sometime in the,
So can it have 2 in there or does it override it?
it can have hundreds in there. Because by default, remember, we don't know how many items are off of an Ethernet port because it's multi-access. Yeah, I agree with that. Through which port will the switch for the frame? Yeah, I agree. EG, I agree. Yeah, that's more intelligible. Instead of what's saying. Where will the switch forward the frame? Yeah, through which port will it forward it? I agree. I agree. Okay. But yeah, somewhere, just like if you look at this MAC address table, somehow on port FA1, the OA host has sent something at one point, OB has sent something, and OC has sent something. So we've got a partial MAC address table that, so this switch is in the process of learning where everyone's at on this. Let's do a new problem. So let's look at this one. So the destination is 0B, the source is 0A. All right. So where will the switch forward the frame? Well, let's look. Where's 0B at? It's on FA3, so it's going to send it over there. And it's going to say switch adds to MAC address, which is currently not in the MAC address table. Well, that's not true because 0A is already in the MAC address table. So that's not correct. Frame is a broadcast. No, it's not all Fs. Frame is a unicast, will be sent out one port only. So that should be the correct answer. And you can keep doing new problems pretty much from here on out. Let's look at this one. Destination MAC is 0B, source MAC is 0C. Now this one's very interesting. So let's see this. So it's going to 0B from 0C. So let's look. Where will the switch forward the frame? Well, let's look at the MAC address table. Can you find the MAC address 0B anywhere in the current MAC address table?
No,
No.
so it should send it to everything except the port that it sent it from.
Exactly. So it's going to send it out FA1. Now here's where people get in trouble. They want to put FA1, 2, 3, 4, 5, 6, 7, blah, 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 blah. It's only going to send it out the ports that have something plugged into it. It can't send it out a port with nothing on it. So to send it out FA1, FA2, it will not send it out FA3. It will not send it out FA4 or FA5 because FA5 is the one it came in on. It will send it out FA7 and FA9. Now, switch adds the source MAC address, which is not currently in the MAC address table. Let's see. Well, is 0C in the MAC address table? No, it is not. So it gets added. And it says the switch is a broadcast. Nope, it's not all Fs. It's a unicast. Nope, it can't be sent to a specific port only because we don't know where that particular MAC address is yet. So it is a unicast frame that is flooded out to all ports. That should be the correct answer. So it's only the ports that have a cable in it. If the cable's not in there, that port's down. So it can't forward it out a port that's down. One more, and we'll stop there. All right, so let's look at this one. Destination 0D, source is 0F. So let's see here. 0D is known. Okay, so our source is 0F, which is down here. 0D is our MAC, so that one is known. So it's going to forward it directly out FA7. The switch has got to add the source MAC address into the table because that 0F is not known to be on port FA9, and it is a unicast frame that's going to a specific port only. Okay. This is a good little exercise to let your students play with for a good amount of time in class, and you need to probably sit there and do it with them just to show them the differences of what happens. Let me see if I can get one that's got an, here we go. Here's a good one. All right. So destination is all Fs. Source is 0D. Where will the frame forward where will the switch forward the frame? Well, it's a broadcast. So it's going to go
So
out.
everything that has a plug.
Everything except the one it came in on. So it's going to come in FA1. It's going to go out FA1, FA3, FA5, and FA9. It won't go out FA7 because that's the one it came in on. Also, it's not going to add the address. So that should be the correct answer right there. port is broadcast and sent out all frames or all ports. Okay. Now, I want to jump over and show you a real switch here. So let's jump over to my lab here. Somebody's working in the CCNP lab. All right. I've made a couple changes here, and I have put a couple IP addresses on these. The PCA is 192.168.10.12. PCB is 192.168.10.11. And then switch 1 is 192.168.12.11, and switch 1 and switch 2 are 12.2 and 12.3. So let's do this. I'm gonna do a show MAC address table. You'll see that I've got some MAC addresses in here. So I've learned some dynamic addresses, and one of them is on port 06. And you'll see that port 06 should be PCA's MAC address. So let's go look. So it's 19.0F. Let's go look over here and see. Config/all. Oops. And you can see my virtual adapter here is wrong one. There it is right there. So there's 12.2. See, physical address is 7EEE. So that is not showing there. All right, let me ping something here. Let me ping across. Let me ping 192.168.12.2. I can go and do that, and that should ping. Guess I got something messed up. Yep, there we go. So I'm pinging the switch itself. Go show MAC address table. We should see. Yep. Now, one of the reasons why we're seeing multiple MAC addresses on these ports is due to the way NetLabs is set up. What you don't see in the background, you are seeing this topology, okay? But in real life, let me show you what's going on back here to give you an idea why you're seeing more MAC addresses than you would expect. Control C, go over here and let me give you a perspective here of what's actually going on. When you are working in NetLabs, what actually is happening is this switch right here, where it shows these two switches connected to each other on 0.1, okay, right there. They're actually connected to what's called a control switch. So there's a control switch up here. This port is actually up here. This port goes to another port, and these two ports get mapped into the same VLAN when the lab gets turned on. And likewise, this port right here is not really going to PCA. It goes up to a control switch port that gets mapped to a VLAN. And so this virtual machine gets mapped to the same VLAN. So this may be a VLAN 10, and this is also mapped to VLAN 10. Likewise, this goes up to a real port, it may VLAN 20, and this is 20. So when I show you these switches and you see that I'm looking at switch 1 and there's 3 different MAC addresses showing on this port FA0106, the real reason is because they are connected to another switch in between. And that's just the only way you can make this work with NetLabs. Now, let me show you this. Let's ping switch 2, 192.168.12.3. Right now, you'll notice if I do a show MAC address table, we don't get anything. We get added into the MAC address table a dynamic address for switch 2, but we also get the port that's associated with the other control switch port. So when you're looking inside of here, you're going to see a couple extra addresses that you won't see in the real world. But if you can still see PCA, which is off of switch 1 with this MAC address of 95.7EEE is off of port 6. 95.7EEE or EEE is off of that port. And it's a dynamic MAC address. So if I go on this one to a clear MAC address table dynamic, and then do a show MAC address, you'll see that I've lost my EEE. I've lost all my dynamic MAC addresses. But just as soon as PCA pings that switch, if I do another show MAC address table, you will see now that the 95.EE or 95.7EE is back in that table, because remember, when it came in, it would have seen the source MAC address and associated it with port 06. Likewise, on this particular PC, if I do an ARP-A, you will see that the IP address 192.168.12.2 is associated with a dynamic entry, and that entry is in my MAC address table for the PC. How did that entry get into the PC? Does anybody know how the PC learned the MAC address of switch 1? Anybody know?
It
It saw
learned
it
the
coming
MAC
through its
address when,
NIC, right?
yeah,
Oh, hold on a minute, Donnie, go ahead.
it learned the MAC address when the switch actually responded to the ARP.
The ARP request, exactly. So when I typed in ping on A, ping 192.168.12.2, if there's no entry in the MAC address table for that IP address, an ARP request goes out and an ARP reply is returned. And then A puts that into its MAC address table and it can build the frame and it can send it. If it can't build that frame, it cannot send it and it will actually fail. Now let's try something neat here. And I showed you this last week, but I want to show it to you one more time just to make sure you're very clear on this. And that is, I'm going to start Wireshark. I'm going to eventually here in a second, once it gets up and running, I'm going to start capturing on my Pro 100. Okay, so we're capturing. Now PCA is going to ping 192.168.12.11, which is the IP address of PCB. Come on. There it goes. So we're getting 12.11. If I go over here and stop this and filter by ARP, you will see an ARP request come through. Who has 192.168.12.11? Tell 192.168.12.10, which is my machine, or was PCA. And then it tells it right there. And here is the reply saying, this is me, and this is the MAC address of, or this is 12.11, this is the MAC address of 12.11. Okay. So pretty cool stuff to actually see it in action. But if I go into the switch table here, again, you'll notice if I do a show MAC address, you'll see it's learned the MAC address of PCB off of 018, but you're also seeing these other items off of 01 because of it being connected to an additional switch. But you'll see how switch 2 also sees PCA off of its FA01 because PCA is off of switch 2's FA01. It's over here on switch 1. So by building these MAC address tables, we are able for our networks to actually filter based upon MAC addresses. Now, inside of the switches, there are two major methods that we do for frame forwarding. One is store and forward, which with this one, it actually brings in the entire frame into the switch, runs the CRC, ensures the CRC is not wrong, and therefore the frame is not corrupted. And then it will send the frame on out the egress port. So it brings it in the ingress port, does the frame lookup, checks the CRC, and then we'll send it out the egress port. Most Cisco switches today use store and forward as the default method for their frame switching. There's another method called cut through switching, and there's two actually subtypes in cut through. There's fragment free and fast. And with fragment free, it brings in the first 64 bytes of the frame, and as long as those are not in any way damaged, it will start forwarding. And the reason being, anything that is at least 64 bytes in size can't be a runt, so it shouldn't be a frame that's actually been damaged. And then there's another one that allows you to do cut through, and cut through is when only as soon as it sees the destination MAC address, the full MAC address, it starts forwarding the frame out the egress. So there's our two variants, fast forward and fragment free. Fast forward is when it gets the full destination address. Fragment free is when it receives the first 64 bytes of the frame, it will start sending it. Switches also have buffers on them so that in the event that, and just in our example alone, or in my example earlier, if there were multiple PCs trying to contact one another. So given our example here, let's say that the source PC on the left, PC on the right, we're both trying to talk to the server at the same time. The switch can actually use its buffers to hold that information. And there's two types of buffers, port-based and shared memory. With a port-based memory, each port has dedicated memory to that particular port for buffering. And in shared buffering, there's a buffer pool shared by all ports on a switch. We've already talked about duplex, half duplex, full duplex. We did not talk about auto cross. This is something I had to explain to my students last week at Skills USA, and that is we had two 2960 switches connected to each other. And by default, typically when you connect two devices to each other that are like devices, use a crossover cable. The one that confuses people is this one. Why do you use a straight through cable from a switch to a router? And that is because on a router, you consider the interface to be a network interface card on the router. But we don't have to actually use crossover cables anymore with modern networking equipment. Modern networking equipment and also iOS version 12.2 or higher uses what's called auto cross or auto MDIX. So it will automatically cross for you without you having to put a crossover cable onto the device. So those are that's very nice. Any questions about layer 2 and about our MAC addresses? Remember, MAC addresses are physical addresses. They're burned into the NIC because now we're going up one layer. We're now going to go up to the network layer. And at the network layer, we are dealing with logical addresses. It has nothing to do with any physical characteristic of the device. We're going to talk in particular about IPv4 and IPv6. These are both layer 3 addresses. And you will see that layer 3 addressing is used for routing and path determination. That's the best way for you to remember what layer 3 is used for. The network layer is for routing and path determination. The IP address, there's an IP header, and as part of that header is the source and destination MAC addresses. Excuse me, source and destination IP addresses, not MAC addresses, IP addresses. And one of the things that confuses people is that IP is a connectionless protocol. It is best effort. It does not care whether or not it gets there. Layer 4 TCP or UDP will determine whether or not it's guaranteed delivery. But at layer 3, IP is connectionless. It doesn't care. A good analogy is a connectionless letter is a letter that you just stick in the mailbox and hope it gets there. If it's connection oriented, you would have someone sign for it on the receiving end. But with connectionless, you throw it in the box, hope it gets there. Best effort, it's going to try to get it there as fast as it can. If it doesn't get there, some packets may be lost. Well, you better hope you've got an upper layer protocol that's going to retransmit those lost packets, which if you're using TCP, you will. And this is probably the reason why all of us use TCP IP now instead of some other protocol. And that is because when they developed the standard for IPv4 and IPv6, they made it completely media independent, which means it'll run over fiber, it'll run over copper, it'll run over wireless, it'll run over carrier pigeon. That's a joke, but there is actually an IEEE April Fool's joke of TCP IP over carrier pigeon. But it does not matter what the media is, IP will run across it. So let's look at an IPv4 packet. Let's look at what the packet looks like. So here is an Ipv4 header. Now look how complicated this thing is. So we've got a version, we've got an internet header length, we've got these two items here, DSCP, differentiated service control point, which can be used for quality of service, total length, identification, flags, fragment offset, time to live. Remember the TTL is that item that every time a an IPv4 or IPv6 packet goes through a router, the TTL is decremented by 1. And when the TTL gets to 0, you chuck it. Quick question. Was there any TTL field in a frame?
No.
No. So that's why, let me show you something that's super dangerous. Show you something that's really, really bad. Imagine this. Okay, you got a switch connected to a switch, connected to another switch with a PC down here. And this PC sends a broadcast that comes up here. It's going to go out this port and it's go out this port, right? Well, when it comes in on this port on the switch up here, it's also going to go out this port. When it comes in this port here, it's going to go out this port. Now it's going to come through and go out this port. And then it's going to come out this port, and then this port, and then this port. And next thing you know, you got a broadcast storm. And since this is a layer 2 storm, it will not stop. The only way that you can fix this is by actually breaking the link. You have to disconnect the cable. So layer 2 loops, we're going to learn eventually about spanning tree. But if you have a layer 2 loop, it is very, 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 very bad. Yep, it's a broadcast storm, an infinite loop. Exactly, Bishop, exactly.
I mean, we always stacked our switches. Why would they be in a circle like this?
Well, they can just be stacked on top of each other and still be connected. I mean, you could just do this. I'm just talking about all I got to do is put a cable here and a cable here and then a cable here to up here. That's still a loop, same thing.
Right. So is that, you know, we would walk in when we would have a loop back and all the lights were flashing. In synchronous, is that what's going to be look like here as well?
Yep, every single one of the lights on these would just be blinking just as fast as they could possibly blink. Yep.
Okay, thanks.
Now, what? Thank goodness, what we actually have is a thing called spanning tree. And what spanning tree is going to do if you don't turn it off is it's going to take one of these ports and put it in a blocking state. Okay, so we'll learn about spanning tree down the road. But STP is a special protocol that will stop layer 2 loops. But the key point I wanted you to realize is that layer 2 has no time to live, so it's not going to ever stop. Yep, and if you use more ports, yeah, exactly. Good, Donnie, very good point. If you use multiple ports between switches for more bandwidth. So if you've got a switch here and a switch here, and you connect 2 ports to one another, trying to get extra bandwidth, you've actually created a loop. What we're going to end up doing, and you will eventually learn in this class too, you're going to learn about doing ether channels where you connect those 2 channels together, and they appear to be one port for the use of spanning tree. Yeah, very good. So this TTL is very important because it will save you in the long run. But then we've got our source IP address and our destination IP address, which in a IPv4 header, they're going to be 32-bit addresses. Okay. Now I want to show you that. Let's look at the difference between all of the stuff in that header, and then let's look at an IPv6 header. Let's look at how much simpler an IPv6 header is. Okay. Now, first off, we're out of IPv4 addresses, so there's no more IPv4 addresses even available to give out unless we're doing private addressing. So we will be moving more and more to IPv6. And let's take a peek at the header. There's IPv4. Now look at the IPv6 header. Look how much simpler that header is. So the way it's been designed, even though the source and destination IP addresses are much bigger, they're 128 bits, so they're very big. But even though they're bigger, the header is simpler, and in many ways, IPv6 can be more efficient than IPv4 because of the ease of the header. Now, I do want to go back up here real quick and show you IPv4 addresses. There's only about 1 billion or so, or actually, let let's see, 32-bit addresses, there's what, about 4 billion or 4,900,000. But look at this for IPv6, there's 340 undecillion addresses, which is roughly equivalent to every grain of sand on the planet. So that's how big the address space is for IPv6. Now, having said that, we'll eventually run out of them, because think about when we have all these nanobots running around, every one of them's got to have an IP address on it. Now, how does a host route? Well, just like a host has a MAC address table, hosts actually have route tables, okay? Okay, so if I do route print, you will see the route table for this host. You will see that this host is actually on the network 192.168.12.0 on link via the interface 192.168.12.10. You also see the broadcast IP addresses associated with this particular machine. And you'll notice there's no default gateway set. So I have no default gateway set on this particular machine. I didn't set one. But you'll notice there's an IPv6 table also, and that is because IPv6 is enabled on this machine, but not, I have not configured an IP address on it, an IPv6 address. So when this machine goes to route, it actually looks in its local routing table to make a decision. So it will look, so let's say that PC1 is going to connect to PC2. It would look and say, hey, 192.168.10.10, that's my IP address. I'm going to 10.15. It actually compares the IP address on it and ANDs it to the subnet mask to determine what network it's on. And then it will look and take the destination IP address and find the subnet that it is on. And if it's on the same as PC1, it will send directly to PC2. If it's not, if it finds it's on a different network, it's got to send it to its default gateway if one has been configured. So to get to the remote host, it would have to go to R1. Now, that default gateway is very important. It's always the IP address of the router that is on the same network as the host and is closest to the host. So the default gateway on PC1 here should be 192.168.10.1. And then that's where PC1 would send its information if it needed to get to the remote host. Now, how would PC1 get the MAC address for the remote host? Does anybody remember that from our discussions from last week? Donnie, you want to answer that one?
Well, ARP.
It would ARP it.
Yeah.
And who would reply? Would the remote host reply?
I think everybody will reply except the specific one he's looking for.
No, the router would reply.
The router will reply.
That's right. That's correct.
Yep. Remember that I told you about proxy ARP. And so when PC1 sends out an ARP, it will go out and it will go to everyone on this link. But R1 will say, oh, that's the IP address for a remote host. So R1 will respond with its MAC address for the remote host. So that's called proxy ARP, because remember, ARPs are broadcasts. So this host makes a forwarding decision by looking in its local table and deciding, is it local? Is it a remote host? And then makes this routing decision based upon that. Likewise, the router will have a routing table and it will know what networks are connected directly to it. So in the host routing table here, you can do it two ways. The netstat-r is one way to do it. I did route print, same thing. Explains to it. Why did we skip IPv5? It was never ratified. Yeah. Yeah, IPv5 was never really a standard. So they just went to IPv6. It was not useless. Yeah. It didn't provide any advantage at all. So they didn't even bother with it. So let's look at routing itself. So a router has a routing table. And so what it does is it learns by looking at what IP addresses are placed onto its directly connected interfaces. And then it builds a route table from that. So R1 would have a route table. And if PC at 192.168.10.10 was sending something over to 10.1.1.10, that packet would come in, it would hit R1. R1 would look at the destination IP address and say, oh, that's destined for 10.1.1.10. Where is that network at? And it would look down its route table and say, oh, 10.1.1.0, that network is available via R2. It would then forward it to R2. Now, some key points here is every router makes its routing decisions based upon its routing table alone, no one else's. Also, just because there's a route to a destination doesn't mean there's going to be a route back. So just because R1 can forward this over to R2 to get to 10.1.1.0 doesn't mean that R2 can get back to 192.168.10.0. Okay, so that's very important to know. And so when we look at these routing tables and we look at how they are, we can have different types of routes. We can have directly connected routes, and those are routes that are placed on the interface of a router. And then we can have remote networks, which are those that are remote and are learned via either static applied routing paths or dynamic routing paths. And then we can have what's called a default route, or sometimes called a gateway of last resort. And the default route is if nothing else in the routing table matches, use this route. Now, if you don't put a default route in and nothing in the routing table matches, the router simply throws that packet in the bit bucket. So a router without a default route will chuck anything that doesn't have a route in its route table. Likewise, a router that has multiple routes in the route table will always use the route that has the longest prefix length. So let's look here at our connected networks. R1 is connected to the 192.168.10 network because it has an interface that has 192.168.10.1 on it. It's also connected to the 209.165.200.224/30 network using the address 225. So those two routes are directly connected. And let me show you something. I'm gonna pull up Packet Tracer real quick just because it's a little quicker. Oops, there we go. I want to show you something kind of neat. When we're looking at routing tables and we're looking at how a router builds its routing table. Let me go ahead and sign in. Come on, let me sign in. Okay. Okay, so I'm in. Eventually, I'll be in here in just a second. Okay, so I'm gonna pull a router out here. So I'm gonna pull out a 4331. I'm gonna pull out a switch because I need a physical connection to be able to bring the interface up and pull out two switches actually. So let me connect here. What kind of cable would I use to connect a router to a switch?
Straight through.
Straight through. Yep, that is correct. So let's do that. And I'm gonna bring this one over here. 001. Okay. So gig 01, and I'm gonna go into the router itself, which should be booting. It's already booted. And I'm gonna do EN. Okay. EN for enable. Should works just like a switch. I'm gonna do a show IP route. Now notice there's nothing in the route table right now. Absolutely nothing. So I'm gonna do a show IP brief to show you there's no IP addresses assigned on any interface. So none of my interfaces have anything on them. So I'm going to go in here and go to config T for global config, interface gig 000, an IP address of 192.168.12.1, my favorite IP address range. Okay. Now, if I do a do show IP route, notice what happens. There's still nothing in the route table. I want to do a do debug IP packet. Do debug IP packet. Okay. Now I'm gonna do a no shut and let's watch what happens. So now if I do a do do show IP route, look what happens. I now have a directly connected route on my gig 000 because I put the IP address of 12.1, which is what this link local or this local address entry means. That, by the way, only happens on iOS version 12 or higher, but you will notice that my 12.0 network is now available on gig 001. Likewise, if I go over to my other, let's go to interface G001, IP add 172.16.0.1, 255.255.255. Actually, let's just do /16. Oops. Let's see if I do show IP route. It's not in there. If I do a no shut now, and now I'll do a do show IP route, you'll see I now have two directly connected networks, 172.16.0.2.
I don't understand the difference between the C and the L.
Okay, the C is the network, the L is the actual IP address on the interface itself. So you see the local address that's actually on that interface is 172.16.0.1/32. So that's the actual address that is on the interface itself. So that's what the L stands for. It's the local address that's on that particular interface. Likewise, you see down here on gig 000, 192.168.12.1 is on that interface.
So the C just defines the network,
The connected
but
network.
the L says this is actually connected.
This is the IP address that I have on that network, correct?
Okay.
Now let me show you this. Let's go a little bit further here. I'm gonna stick router here. I'm gonna connect. I'm gonna connect this one, gig 00 over here. Okay, that is gig 00. Yep. All right, so we're gonna do this. We're gonna go en config t int g00 00, and I'm gonna do IP add 192.168.12.2. So I'm putting it on the same network as the gig 000 on the first router. And if I do, I'm not also going to, let me drag out one more switch here. And this is where Packet Tracer has some cool features where you can just do some real quick little summaries here, or quick little examples. Let's do int gi0/1. I'm gonna give an IP add of 10.0.0.1 255.0.0.0. No shut. Now let's do this. Actually, let me real quick. Config t host s2. Control Z, right. Let's make this host s1 r1. Why in the world I do right? Okay. No, why in the world I'm a doofus. I called it a switch, but config t host r2. Okay. So let's look here. Let's do a show IP route, and you'll notice that there's two connected networks to 10 and 192.168.12. So I'm going to ping 192.168.12.1, which is the IP address over on R1, and you see it's successful. So I can ping from router 2 here over to router 1. Let me bring up router 1 here. I'll show you this one. So, but now you'll notice, this was in chat. That's kind of a good way to look at it, Bishop Ransom saying L is your complete home address, C is just your street name. Yep. That's a decent way to look at it. All right, so let's go and look now. So R1 and R0. So what if I try from I'm actually let me drop all that here. Undebug all. Let's turn that off. What if we try to ping the gig 01 interface over on router 2? So you see it's at 10 network. So 10.0.0.1. What do you think is going to happen? It's going to time out.
Not gonna come back.
Yeah, it's not going to work. It's not even going to go because what's this? Let's do, once this times out here, let's do a show IP route. Is there any route in the routing table for the 10 network?
No.
No. So when it does a lookup, when I try to ping 10.0.0.1, R1 does a lookup, it looks in the route table. There's no network there for the 10, it drops it. Okay. So I can fix this in a variety of ways. I'm going to add a static route. So I'm going to go config T IP route 10.0.0.0 255.0.0.0 and next hop IP address is 192.168.12.2. Now, if I do a show IP route, look what we've got now. We now have a static route going over to 12.2 to get to the 10 network. So if I ping that now, it works because it has a route over there. You'll notice though, I cannot ping the 172 network from R2 because there is no entry in R2. So I can put a static route on R2 going back. But I'm gonna do something a little different. I'm actually gonna do this. I'm gonna go in real quickly. It's a very simple thing to do. I'm actually going to do a real quick routing protocol. I'm going to just do, this is OSPF. By the way, by the time you get done with all 3 classes, you'll be able to do this same example yourself for your students very quickly. Right now, you don't need to know how to do this. You just need to realize that I'm showing you a dynamic routing protocol. So I've shown you a static routing protocol or static routing by using a static route. Now I'm going to show you a dynamic routing protocol. Now I should be able to show IP OSPF neighbors, unless I mess something up. Show IP OSPF neighbor, and we've got a neighbor. And now we'll do a show IP route, and look what's happened. Well, should have. Let's give it a second. Show IP OSPF neighbor. Can't type. Okay, it's still getting there. It's an X start. It's got to get all the way into. Unless I mess something up here. Nope, there it goes. Now we're full. Once it gets to full, it's fully up and running. So now let's look at the routing table. Show IP route. Look at the new route we've got now. We now have a route to the 172.16.0.0/16 network. That was dynamically told from R1 to R2. It said, hey, I have this network available off of my Ethernet. And now we could ping from R2 over to 172.16.0.1. We have full connectivity. So on R1, we have a static route going to the 10 network on R2. And on R2, we have a dynamic routing protocol, which is coming back to R1's Ethernet. So these are multiple ways that a router can route connected networks, statically defined networks, dynamic networks. And now I could also do a default route. And with a default route, it says, and if you look at our network, default routes actually kind of make sense because the only place that R1 can send anything is over to R2. So I could actually, instead of doing a static route to the 10.0.0 network, I could change this and say no IP route I'm getting rid of the 10.0.0.0 network. And because remember, to get rid of most commands, we just use the no form of it. I could do IP route. This is a default route, quad zeros, quad 0. And I could go 192.168.12.2. And so now if I do a Control Z and do a show IP route, it says anything that I don't know how to get to it, use the static route. Okay, right here. So anything I don't know how to get to, send it there. But you'll notice I've actually learned the 10 network via OSPF now. Because I'm also running OSPF, but if I ping 10.0.0.1, we are successful. So what I got in chat here. So I don't have anybody. Okay, Michael, that's fine. No problem. No problem, Karen. But that is how devices, how routers route. They can use a static route. They can use dynamic routes. They can use default routes. And all of that is part of this routing table here. And I just basically showed you, you can go back over all of this information now after I've shown you kind of my examples. And hopefully the way I showed it to you and also reading this will help it make sense to you. Right? Are there any questions? Okay, Wednesday we'll be going over basically 9 and 10. And I did have a good question. Somebody asked, if I'm done with the reservation, how do I end it? Well, you just go to reservation, end reservation now, and then click yes, and the reservation will end and it will clear out everything that's taking place. Okay. I'm gonna stop sharing. No more questions. Everybody's good. Let me turn off my recording.